Hello everyone. In this video we will continue to examine topic 2.1 motion, and in particular we will continue to examine velocity time graphs. Alright, return to a velocity time graph, but in this case we're going to examine a velocity time graph of a constantly accelerating object. This is a case of constant acceleration. Consider a car moving initially at plus 6 meters per second that accelerates at a rate of plus 2 meters per second for every second for 5 seconds. Okay, so this car is gaining 2 meters per second every second for 5 seconds. The first question is, what is their final velocity? Right? What is their final velocity? Well, if they're gaining 2 meters per second every single second for a total of 5 seconds, then you know that they will have gained positive 10 meters per second over the whole trip. And so plus 6 meters per second plus 10 meters per second over the whole trip gives you positive 16 meters per second. Right? Notice that we can formalize this process, okay? This process of thinking about the acceleration to find a final velocity. If the acceleration is equal to the change in velocity over the change in time, as it is for any instance of constant acceleration, then the change in the velocity is the acceleration times the change in time, which is what I did implicitly when I took 5 seconds multiplied by positive 2 meters per second and came up with positive 10 meters per second as the change in the velocity in this particular instance. Notice that I can further break up the change in velocity as v final minus v initial and solve v final is equal to the initial velocity plus the acceleration times the change in time. And this is the formalization of the calculation we did right at the beginning in considering what the final velocity would be. Notice that in red, all of this relates to the graph of velocity time. So here, our object starts at positive 6 meters per second and accelerates to positive 16 meters per second. And in that time, undergoes a change in velocity of delta v, given by this particular distance, over a time interval delta t. Notice that the acceleration is, in this case, the change in the velocity over the change in time, so this quantity divided by this one, or the slope of the velocity time graph. The acceleration is dv dt, just like the velocity is dx dt. So the velocity is the slope of the position time graph, and the acceleration is the slope of the velocity time graph. So we can read the acceleration off of our velocity time graph simply by calculating the slope of this line. But that's not all we can get from our velocity time graph. The other piece of information we can get from our velocity time graph is the displacement, and we can consider the displacement or figure out the displacement by remembering that the displacement is the area under the curve for the velocity time graph. So the area indicated by these blue arrows here, or blue shaded regions, is the total displacement. Now, how do we find that? Well, typically in this class, you could integrate if you know that technique from calculus, but if you don't, that's fine. You're just going to calculate the area of these shaded regions here. Okay, the area of this rectangle and the area of this triangle. The area of the rectangle would be the time interval, 5 seconds, times this particular height, or initial velocity of 6 meters per second. And the area of this triangle would be 1/2 base times height, where 1/2 base is just 5 seconds again, times 1/2, times delta v, 16 meters per second minus 6 meters per second, or positive 10 meters per second. This gives a total displacement of positive 55 meters. Notice that you can conceptually think about this as the displacement due to the fact that you were initially moving at 6 meters per second, and the extra displacement you get because you're speeding up. Okay? Notice this would not be the same displacement as if you had a constant speed of 16 meters per second the whole time. And in fact, this portion of that displacement is exactly half what it would have been if we had started at positive 16 meters per second. That is, when you accelerate, you pick up sort of half the available displacement, or lose half, depending on the direction of the acceleration. Notice that if you have a negative acceleration here on this graph, and you're starting from positive 16 meters per second, you would be slowing down, as that acceleration would indicate that the velocity were changing in the negative direction and going from, for example, positive 16 meters per second to positive 14, positive 12, etc. Okay. Now, in this particular example, I would encourage you to, at this point, calculate the acceleration for each segment, okay, and think about what is happening at each segment. You can then find the total displacement of this particular trip. So this is a trip of a person or an object. It's a person, I guess, in this case, on a bicycle. I would encourage you with a velocity time graph, strongly encourage you to sort of annotate it with what is happening at any given time. So if we take a look at our velocity time graph, right, we can see the velocity is increasing in this region. It's accelerating and speeding up in the positive direction. And then it's going at a constant velocity for this region of time. And then it's slowing down, but still going in the positive direction in this region. And then at this point in this region, it's standing still. And then finally, it turns around and begins to undergo a negative acceleration, speeding up. So this is acceleration in the negative direction. Notice that delta V is -3 meters per second per, let's say that looks like 10 seconds, okay? So -0.3 meters per second it looks like during this region of time. Then the bicycle goes at a constant velocity for this region of time in the negative direction, and then finally begins to slow down. Notice this is a case of positive acceleration, but negative velocity. So this case is positive acceleration, but negative velocity. And we'll see this more in class. Notice that you can find the area in between the graph and the x-axis by splitting these shapes up into triangles and rectangles, areas of constant velocity motion and areas of accelerated or uniformly accelerated motion. And if you add the total area here to the total area here, you can get the total distance traveled. If you note that this area here would be negative, you can subtract it and get the total displacement by taking the total positive distance in this particular case times the total negative distance of this particular case. And as I said, we'll see that more in class. So I would recommend go ahead and calculate the acceleration for each region of time, as well as the distance/displacement for each time interval as well.